Hey, take a nice deep breath. Really. Today, we're going to conquer real numbers together. Think of me as your private tutor sitting right there beside you. We'll take it step by step. And look, before we touch a single formula, you gotta know this exact math is literally running your everyday life right now. E-commerce apps calculating your shopping discounts, surveyors measuring land, architects drafting up building designs, and even your phone encrypting your private data. They all rely on the fundamental rules of real numbers. So, let's just dive right in, and we'll start by looking at the visual logic behind the math. No need to stress, you've got this.
Okay, to start things off, I want you to completely change how you look at numbers. Instead of seeing prime numbers, 2, 3, 5, 7, as these abstract, scary digits, I want you to picture them as fundamental building blocks, kind of like colorful, indestructible little bricks. Let's say a 2 is a red brick, a 3 is a blue brick, and so on. So the big question is, can we build absolutely any other number out there using just these basic prime number bricks? Well, let's look at a visual pattern before we worry about any formulas.
Now, what's super interesting here is how this totally proves our building block theory. Let's just take the number 24. Imagine physically breaking it apart. You could split it into 2 times 12, right? Or, hey, maybe you see it differently and you split it into 8 times 3. But if you keep smashing those pieces down further and further until you just can't break them down anymore, until you hit those indestructible prime number bricks, look what happens right at the bottom. No matter how you started, you always end up with the exact same base building blocks. 3 2s and 1 3. It's like magic. And you know that beautiful visual truth we literally just saw? Well, math actually has a pretty fancy name for it. It's called the Fundamental Theorem of Arithmetic. But please, do not let that formal textbook wording intimidate you. This theorem simply proves what we just watched happen. Every single composite number has its own unique prime number fingerprint. Just like you have a unique fingerprint, the number 24's fingerprint is always exactly 3 2s and a 3. The order doesn't matter one bit, the blocks themselves are always exactly the same.
All right, let's put this into practice with our very first problem. We're going to start with an easy warm-up just to build up your confidence using this whole building block concept. Here's how we approach any exam question. First, what is given? Well, we are given the number 27,300. Second, what is asked? We need to find its prime factorization. Basically, we need to uncover its unique fingerprint. So let's solve it step by step together.
So if we slowly divide 27,300 by our prime numbers, starting right from the smallest, we get a 2, then another 2, a 3, 2 5s, a 7, and a 13. Now, right here is where I really need you to pay close attention, because this is a super common mistake students make in exams. A lot of folks just stop right here. But to get full marks, you need to group those repeating numbers into powers, and you have to write them in ascending order. So we combine the 2 2s into 2 squared and those 2 5s into 5 squared. So our final perfectly polished answer is 2 squared times 3 times 5 squared times 7 times 13. Look at that. You just cracked the genetic code of 27,300. Okay, let's move on and see how this logic builds into slightly more complex territory. We're going to look directly at an example pulled right out of your textbook. I really want to show you this, just to prove to you that you are fully capable of handling official, standard exam material. You literally already have all the tools you need. So here is our medium difficulty tier. What is given? The numbers 12 and 18. And what is asked? Well, we need to find the highest common factor, the HCF, and the lowest common multiple, the LCM. Now, deep breath. Don't worry about memorizing complex formulas just yet. HCF and LCM just use the exact same prime fingerprints we already know how to find. Let's solve it. First things first, let's write out those fingerprints. 12 is 2 squared times 3 to the power of 1, and 18 is 2 to the power of 1 times 3 squared. Now, the absolutely crucial point here is understanding why the rules for HCF and LCM actually work. For the highest common factor, we only want the bricks that both numbers share. So we look at the common primes and we grab the smallest power. They both share at least 1 2 and at least 1 3. So 2 to the first power times 3 to the first power gives us 6. Now for the lowest common multiple, we need enough bricks to build either number completely from scratch. So we have to take the greatest power of each prime. We need 2 2s and 2 3s. That's 2 squared times 3 squared, which gives us 36. Now, the biggest trap students fall into here on the exam is swapping these rules around. Just remember, HCF is what they share, so think small. LCM has to cover absolutely everything, so think big. And this brilliantly illustrates one of the absolute most beautiful symmetries in math. Check this out. If you take the HCF we just found, which is 6, and you multiply it by the LCM, which is 36, you get 216. Now look over at the other side. If you just multiply our original two numbers, 12 and 18, you also get 216. No way, right? It always perfectly matches. The product of the HCF and LCM always equals the product of the original numbers. It is a fantastic built-in way to check your work during a stressful test. You are doing amazing, by the way. So let's step it up to a hard, board exam level question. What is given here? A number in the form of 4 to the power of n, where n is any natural number. Okay, and what is asked? Can this number ever end with the digit 0? Now, please don't panic at the sight of letters mixing in with numbers. It's totally fine. We don't need to guess, and we don't even need a calculator. We just need to use our trusty prime building blocks to solve this puzzle. Let's just think about the underlying logic for a second. For any number in the universe to end in a 0, like 10, 20, or 50, it has to be divisible by 10. And to build a 10 out of our prime bricks, well, you need a 2 and a 5. That is the golden rule here. So let's look at our number, 4 to the power of n. Let's break that 4 down into its prime blocks. 4 is just 2 squared, right? So 4 to the power of n is really just 2 to the power of 2n, meaning it is entirely 100% made of 2s. The 5 is completely missing. And because of that fundamental theorem we talked about earlier, we know this fingerprint is completely unique. No 5s can ever just magically appear out of thin air. Therefore, since the fingerprint totally lacks a 5, it is mathematically impossible for 4 to the power of n to ever end in a 0. See? Look at you! You just solved a board-level logic puzzle. You have worked through some seriously tough concepts today, and your focus has been absolutely stellar. So as a little reward, I want to show you a shortcut straight from the source text that honestly feels like a magic trick. It's going to save you massive amounts of time on your exams. So how would you like to predict if a fraction creates a clean, stopping decimal or a messy, endlessly repeating decimal without doing any long division at all? Sounds pretty good, right? Okay, here is the secret, and it's just brilliantly simple. All you have to do is look at the denominator, the bottom number of a simplified fraction, break that denominator down into its prime building blocks. If those blocks are only 2s, or only 5s, or a combination of strictly 2s and 5s, that decimal will cleanly terminate. It'll just stop, like 16 over 125. 125 is just 3 5s, so boom, it terminates. But if any other prime number sneaks its way into that denominator's fingerprint, like a 3 or a 7 or an 11, that decimal will stubbornly repeat forever. Take 1 over 7. The denominator is 7. It's obviously not a 2 or a 5, so it becomes 0.142857, repeating infinitely. Just check the bottom primes, and you literally know the future of that decimal. Before we wrap up, I really want to congratulate you on your incredible progress today. Let's lock in everything you've learned with this quick 5-point exam cheat sheet. Number 1, primes are the unique building blocks of all composite numbers. 2, for HCF, use the smallest powers of common primes. 3, for LCM, use the greatest powers of all primes. 4, the golden rule to check your work, the product of the HCF and LCM always equals the product of the two numbers. And 5, our magic trick. Denominators built only of 2s and 5s guarantee terminating decimals. Seriously, take a mental picture of this information and you'll walk into your exam feeling totally prepared. You have mastered the building blocks. You've outsmarted those tricky HCF and LCM traps, and you've even learned how to predict the future of decimals. You should feel incredibly proud of the confidence you've built up today. But I'll leave you with this one final thought. Today, we only really looked at rational numbers, numbers that play nicely by the rules. So if these rational numbers behave this predictably, what kind of chaotic, beautiful rules do you think irrational numbers, like the square root of 2 or pi, actually follow? That is a wild world waiting for you in your next study session. Keep that curiosity alive and happy studying.